Well, hello and good morning, everybody. This is Jeremiah. Hope you're ready for another webinar. We're going to get into some irrigation topics today, all about the data. You know, they're saying that the best irrigation design is only as good as the controller. And how do you make a controller better? They're accessing data. I mean, it's where obviously technology is leading. Big data is what us programmers call it. You know, being able to make anything smarter by accessing more data over the internet. And so Chris Wright with Baseline is going to show us some pretty cool stuff. Couple quick things to mention. I always mention this at the top of the screen there. There's a little thing that says view options, and you can exit full screen mode. I always do that because otherwise it takes up my whole monitor and it drives me crazy. So that just frees up a little space on my monitor. So I like doing that. But do notice you have that question box, the Q&A box. Please get your questions typed in there, and we'll definitely get that answered and get those over to Chris. And I think that's about it, but definitely be sure and get your questions in as those come up. We're happy to answer questions. It's definitely tended to be interactive. And I think that's enough of my yipper-yapping. I'll get this over to Chris.
Thank you very much, Jeremiah. I hope everyone is doing well today, and I'm excited to be presenting to you this fine day regarding data-driven smart watering. You know, smart watering has become the new standard and expectation in the irrigation industry, as specifiers and end users alike are looking to utilize technology in order to apply the right amount of water to the landscape to achieve aesthetic value and also conservation objectives. So what I want to address with you today is data-driven smart watering and how you as a specifier and a designer can identify, products or technologies that can be utilized by an end user to water correctly, prevent overwatering of plant material, and achieve conservation objectives as water is becoming more and more valuable of a resource in the landscape. So as we look at the methods or technologies that are available to an irrigator for smart watering and water management, there's several different methods that they have at their disposal. One of them would be visual, just putting eyes on sight. Another would be utilizing a soil probe to get an indication as to what is happening below the surface of the soil or surface of the landscape. Another would be using instrumentation, devices like a weather station, to get an environmental indication as to what's happening so that a controller can make a more educated decision in how much water it needs to apply. And then there's also subsurface sensor technology that can be utilized to get feedback or data from a site to help make irrigation decisions based on frequency of irrigation or duration of irrigation cycles. So as we look at these different methods or technologies, what data do they provide to the end user? If we look at the first method, which is eyes on sight, that really gives the user empirical data as to what is happening with the landscape aesthetically. Seeing is believing, and being able to recognize when a stand of turf requires irrigation in order to retain its aesthetic value, that can be a very effective way to conserve water. However, it's not very practical because it does require going to the site in order to make those irrigation decisions. They're limited because they're not able to see the amount of moisture that is in the soil profile below grade. And then the water time is oftentimes an opinion as to how much water needs to be put down in order to properly hydrate that stand of turf. Taking it a step further, looking at a method that gets into a bit of technology would be using a soil probe. Again, it gives us empirical, seeing as believing data or visual as to how much water may be in that soil profile below grade. But it also assumes that, the user has a knowledge of different soil types and the water holding capabilities of that soil profile. It also requires going to the site in order to take this kind of measurement. Where the sample is taken on the site can be a specific indicator, which may not reflect the water need for the entire site. And again, it's an opinionated runtime as to how much water should be put down in order to replenish that soil profile. As we look at a weather station, this gets into the technology aspect of smart watering, where we're measuring environmental effects of a site or a region or an area, and using that environmental data to automate and calculate a runtime for the controller. The cons of weather station data would be, oftentimes it's global and it's not really representative of the site specific nature of that landscape. And it may not take into account, all the microclimates that may exist on a site, nor rainfall events that may have happened on that site, as opposed to the local area or the region. Another problem with weather data is that it's not real-time data. Usually controllers interfacing with a weather station are getting weather data once daily as a reflection as to what happened the day prior to the next needed irrigation cycle. While it's much better than visual or soil probing a site because it automates it and does not require a site visit, it's a good way to water and better than the two previous methods, and introduces that technology to an irrigation system. Another technology or method would be utilizing a soil moisture sensor in that soil profile that measures how much water is being applied or being depleted out of that soil profile in real time. It's very site specific. It's very reportable and graphical at any given moment, so a user can get an at a glance status once they access the sensor to see how much water is available to the plant material. And it's smart enough to know when to start or stop an irrigation cycle. But some of the issues surrounding moisture sensors would be that they're buried and not visual, so you lose that empirical connection to the technology because you can't see it working in the landscape. The placement and installation is important so that you're getting a true representative snapshot or representative data of what's going on in the rest of the landscape. And then what if that sensor goes bad and discontinues operating or working? How does the controller know what it needs to do in order to continue to maintain the health and vitality of that landscape? So some of the key concepts to consider when we're applying technology to irrigation is a concept known as available water. Available water is the difference between field capacity, which is the maximum amount of water the soil can hold, and wilting point, where the plant can no longer extract water from the soil. Another concept to consider would be the water holding capacity, how much water the soil can hold at field capacity. And then the water use of plant material is evaluated based on the total amount of water required for growth and transpiration, or water loss from the leaf. plus the amount of water lost from the soil surface, which is evaporation. So as we're looking at applying science or technology to irrigation and trying to retrieve data that's helpful in this process, we need to understand how much water that soil can hold and how much water that plant is actually utilizing. So as we look at the soil profile, many of you are familiar, I'm sure, with the textural triangle of soil that identifies different soil types, such as clay or loam or sand. And those soil types are identified to by their particle size. Gravel obviously is going to be much larger particle size than sand, silt, or clay, but our soils are made up of a mixture of these different particle sizes that identify the soil type, and then these soils are classified on the relative proportions of those particles in a sample. So when we think of soils and field capacity, how much water a soil can hold or be held in the media in the face of gravity, we need to think of it as analogous to a sponge. If I take a sponge and I put it in a bucket of water and submerge it until all of the bubbles stop, and I pull that sponge up into the atmosphere, the excess water will run off that sponge and drip off of it until that sponge reaches a field capacity state, which means that it's holding all of the water that it can in the face of gravity. If I squeeze that sponge, water will come out, and as that sponge is exposed to air, water will evaporate from it. But the key concept is that when that sponge is at field capacity, that means that the plant material would have access to that water and be able to utilize it. So then that brings into question an allowed depletion scenario, whereas how much water do we want to dry down to maintain plant health or aesthetic value before we reapply water through an irrigation system? As we look at allowed depletion, it can be dependent on many environmental factors: how hot it is, how windy it is, what the solar radiation intensity is. It can change dramatically in a short period of time. So the hotter it gets, the quicker it'll dry out. But mix that with wind and it will dry out even faster. Or if we're dealing with a soil profile or a landscape that's not on grade, but maybe on structure, like a green roof or a green wall, then that can change dramatically, even more severely, because of the shallow soil profile and some of the wind effects that occur on a building structure. On the opposite, that depletion may not change much over a long period. If we have a flat, very heavy soil where it's predominantly a clay structure, that water can be held in that soil profile for a very long time. And we need to regulate how many irrigation cycles are actually being applied based on how much water may be in that profile over a long term. When it comes down to it, allowed depletion is really the opinion of the landscape manager. If I'm managing the turf in front of a high-profile country club, my opinion of allowed depletion is going to be different than the person managing a native landscape that's outlying around a campus situation where it's not as visually important. So everybody has their own opinion as to what allowed depletion is and when irrigation needs to happen in order to maintain that aesthetic value. So if we look at field capacity versus allowed depletion graphically, The difference between field capacity and allowed depletion in coarse sand is much tighter than the difference between field capacity and depletion in a heavy clay. So we need to monitor or manage those depletions carefully in order to achieve our objectives. Moving beyond the soil to plant water use characteristics, plants are as variable as soils. So the same plant planted in 3 different soils will have 3 different water use characteristics. If we look at the same plant planted in the same soil with 3 different fertility levels, they'll likely have different water use characteristics. And a healthy disease-free plant will have different water use characteristics than the same stress plant in the same soil conditions. Okay, so now we're starting to get into factors that could affect water use and that depletion in the soil profile that can't be accounted for with a weather-based type control system. So we need to measure different data in order to achieve our objectives. So as we look at ET in evapotranspiration, I'm sure all of you that are watching are familiar with what the definition of evapotranspiration is. And as we look at this technology and this science as we apply it to irrigation controls, this is the Penman-Monteith formula for evapotranspiration. And I would encourage all of you to write this down because we'll be tested on it later in the presentation. But you can see it's a rather complex formula that requires a number of inputs and quite a bit of understanding of what those inputs are in order to generate a usable result. So as we're using ET to automate irrigation, what does ETC actually give you? Do you have all the data needed to make a good irrigation decision through this ET formula? Does it take into account rainfall? Does it take into account the soil type, compaction, and slope? What about how the system applies the water, the precipitation rates, and DU? We can achieve that. And there's inputs that are put into the control system to accommodate these different factors. But we need to make sure that our measurement is correct and accurate, and our inputs are accurate and detailed enough so we're providing the data to the controller so it can make a smarter irrigation decision. A little bit more to consider when we look at an ET equation, and as we're looking at historical ET versus real-time ET, is if the historical ET bell curve is followed, we also have some pretty dramatic increases that can happen with minimal inputs. So if we look at this historical ET curve from San Diego, the evapotranspiration rate goes from 1.55 to 9.3 with only 12 degrees of temperature change throughout the season. So we got a drastic change in water requirement without a whole lot of temperature change, especially if we look at daytime versus nighttime temperature changes. But as we look at it a little bit differently or deeper regarding different plant materials, the crop coefficient for a deciduous tree has a much different historical bell curve than standard turf grass would. And the water requirement for a deciduous tree is much higher while it is putting on its leaf canopy than it is throughout the hottest time of the season when it is working towards dormancy. So being able to account for these different growth periods and different water need periods for different plant types requires more data and more inputs be put into the control system to do a better job of irrigating. So as it relates to weather interface, Baseline provides a solution in the form of weather access for Base Manager. And this weather access capability comes with a Base Manager Plus subscription. So if a user has Baseline controllers installed on a site and it has that controller or controllers connected to a network, and that network has access to the internet, then this weather access capability is available for use without any additional hardware components or subscription fees associated with it. With weather access, it gives us the ability to provide those inputs for the site as it relates to sprinkler type or plant type or soil type and slope. And it gives us the ability to use specific species factors so that we can accommodate for density factor or microclimate factor throughout the different times of the year by month, so that we can, as closely as possible, follow the natural ET bell curve for different plant materials. And as a result, you get variable run times that will be executed on the controller depending on those different environmental factors that were happening within any given time frame. Now, for those of you that know Baseline and know how we came to the industry and the fact that we have built our business and our control system around soil moisture sensors, may ask, why are we doing weather now? And the answer is simple, in that by incorporating weather into our control system, Baseline was able to achieve the WaterSense label criteria from the EPA, which allows us to be installed on more projects in more cities in more water restricted prone areas. So we're very excited about this capability. We've been doing it for just over a year now, and it's working very well for us. As we move into our core technology and the data that can be provided through soil moisture sensors, Baseline feels that it's the correct instrument to use in smart watering to make the best irrigation decisions. And we know that if you're not measuring what is happening in the landscape in real time, you really can't manage that site to meet expectations or conservation objectives. Now, the way that the soil moisture sensor works and how it generates data that's used in irrigation scheduling is that in the sensor blade, there's a wire path that we send a high frequency pulse of electricity through and measure how long it takes to travel that wire path. And when the soil is wet, that signal travels slower. And when the soil is dry, that signal travels faster, because that pulse of electricity through capacitance gets into the surrounding soil profile where that sensor is buried. And we're able to put that information into an algorithm that gives us an accurate and repeatable real-time measurement of that moisture content in that soil profile. So much like light traveling through water, if you're cleaning a pool and you stick the strainer in the water, that long pole looks like it bends once it gets below the surface of the water. And that's because light travels faster through air than it does through water, so it creates that refraction. So very much the same principle in play in the baseline moisture sensor technology that allows us or enables us to measure that moisture content of that soil profile. When sensors are installed, that moisture sensor is seeing those applications of water, and we're able to measure how long it takes for that application of water to infiltrate that soil profile and impact the primary water use root zone area of that turf grass or other shrub or tree in the landscape. If we look at a real-time moisture graph of an analysis that was done for a contractor in Las Vegas, Nevada, we can illustrate and see how long it takes that application of water to infiltrate a 3 to 4 inch depth of soil in the landscape. So in this example, the irrigation system was set to water every day at 11 p.m. And this graph shows the increase in moisture content due to that irrigation cycle and the subsequent dry down over the next day until that next moisture or start time at 11 p.m. the following night. And the process just keeps repeating itself. So in this situation, we installed a moisture sensor and set a depletion percentage at 26.1%. And you can see at 11 p.m. the next day, it had not depleted below that threshold line, so it skipped an irrigation cycle. So on the following evening, start time, it was below that setting, and the system came on and it applied 40 minutes of water, and that moisture reading at start time was 24.7. Well, as the system ran, the zone where the sensor was buried stopped watering at 12:27 a.m. and the moisture content was at 26.2. And the moisture level did not peak until 6 a.m. at 32.04%. So we can see that it took 5.5 hours for that application of water to reach its peak before it started to deplete down again. So this gives us a good indication not only of how long the water takes to infiltrate that landscape, but it also can help us with data to determine if all of that water was necessary to be applied to maintain the aesthetic value of that turf that was required. So this kind of data and being able to visually reference it and measure it and graph it can help us make better irrigation decisions. So as we look at sensor placement and how to apply that technology in the landscape, you want to obviously take into account microclimates that may exist on a site, and you want to break that site up by water need. So we're hydrozoning a site based on sprinkler type or plant type or exposure, and then identifying a zone within that hydrozone that's representative of all the zones in that hydrozone, and burying a sensor in it and using data from that sensor to irrigate that entire hydrozone. So when this zone needs water based on my allowed depletion setting, then the rest of the zones in that hydrozone will also irrigate for the same amount of time. So burying the sensor in the active root zone of the plant material, and again, shallow enough so that the sensor can see irrigation cycles in a timely manner, can help us really monitor and manage how much water needs to be applied in order to maintain that healthy turf. So when used properly, the soil moisture sensor acts much like a thermostat in a building application, where it's taking into account all of the different factors that are changing that environment to maintain a desired moisture content and or comparatively temperature in that environment, so that the plants are healthy and happy and not getting overwatered in the process. When using this data and applying it to an irrigation cycle, the most common watering strategy would be a lower threshold strategy, which means that the lower threshold tells the system to turn on based on soil moisture content and then turn off based on time programmed into the controller. So this literally controls the frequency of irrigation cycles to promote a deep and infrequent watering scenario that is often referred to as the best management practice for irrigation of landscapes. So when this strategy is applied and utilized, this is a moisture graph of a system during August of 2015 in the high deserts of Utah, where there were extreme temperatures and quite a bit of thunderstorm activity that occurred during that month-long period. So in this system, a lower threshold strategy was set at around 24%, and anytime a start time came up on the controller, if that moisture content was below that threshold setting, then it would allow the irrigation system to come on and operate for whatever time was programmed on it, and all other zones that are linked to that sensor would operate in the same manner. So in this case, there were 6 of 31 scheduled days that actually watered in the month of August. The historical ET for the month in Salt Lake City, Utah is 7.4 inches. The area irrigated was 2,500 square feet. And if we do our CLIA math, we can calculate how much water was required and how much was actually applied, and calculate how much water was saved based on how much time was programmed in the controller to operate without using that data or that technology. So 71% of the water was saved that was scheduled to irrigate for that time frame. So let's look at a more extreme example with the growing popularity of green roofs and green walls in our industry and profession. How do we use sensor technology and data to monitor this application effectively? So Baseline also manufactures a small compact sensor that is designed for these type of applications that allow us to insert them into that growing medium and create hydrozones for those panels of vegetated area on the building structure. So in this case, 3 different zones were created on each one of these panels, top, middle, and lower, and the sensors were measuring real-time data throughout the day to help make irrigation decisions based on what the water need would be of these plant materials at these different levels. Obviously, gravitational drainage is a big factor here. So would the bottom of the wall require as much or as frequent of watering applications as the top of the wall? So if we look at the moisture graphs and the data from these moisture sensors, the top of the wall was set to operate at 4 different start times throughout the day. Each start time would allow the controller or that zone to run for 15 minutes. A lower threshold was set at 24% depletion. And you can see that in most cases, that top of the wall zone on that system was irrigating all 4 start times throughout any given day. If we look at the middle of the wall, due to gravitational drainage and the fact that the exposure isn't as extreme in the middle of the wall as it is at the top of the wall, 2 different start times were programmed to the controller with a shorter run time at a lower threshold setting, and then that zone would only irrigate if it dried down below 21% moisture content at either 8:30 or 9:30. So you can see that it started to wean off of the amount of irrigation required in order to maintain that desired moisture content. And then if we look at the bottom of the wall, the gravitational drainage was allowing the bottom of the wall to get an adequate amount of water so that the last or the bottom zones were not irrigating at all, saving that water and not over applying water to that soil medium in that wall. Okay, the second type of watering strategy that we can use, and the data from the sensor can be utilized to determine how long a zone should run in order to retain a desired moisture content in a soil profile. So in the upper threshold strategy, the user tells the system when to run, and then the sensor will turn the system off based on moisture readings from that sensor. So you can get a variable runtime from this scenario based on how much evapotranspiration was occurring out of that soil profile at any given time. So as we look at the sensor technology from a specification perspective, the sensors are not just for turf, shrubs, and beds. They can be used for different applications and are increasingly used as level indicators in secondary water sources such as cisterns and ponds to help regulate and manage water sources. So there's a significant amount of information available on the Baseline website that can be referenced to learn how to use the sensor technology and get data from those sensors in order to help, irrigate the landscape, but also manage water sources at the same time. So the website is baselinesystems.com. There is a specification tab designed especially for designers that provides all kinds of different information regarding the product and applications of the product. So with that, I'd like to thank you for the opportunity to present to you today. And please, if you have any questions or would like more information, you can contact me directly and I can help you or refer you to a regional manager that works in your area to help you support you in your specification. So thank you very much.
Oh, hey, that was really cool, Chris. We do actually have a few questions if you did want to answer some now.
Okay.
Got a handful of them, so get ready. Got a really
Perfect.
good. A real quick one. On that, on the wall, you showed the 3 different sensors, but a related question was, how large of an area for the standard size sensor would you recommend for each sensor?
Okay, that's an excellent question. And the answer is really how much area you would like that sensor to monitor and measure. So the technology is set up so that in the controller interface, the zone that has the sensor buried in it becomes a primary zone. And then you can link like zones to that primary zone, and the linked zones will operate in the same manner as the zone with the sensor buried in it. Okay, so you're creating that hydrozone, oftentimes identified by programs on the controller that say, when this zone waters, I want these other zones that are associated with it to water as well. And that can be one or two other zones, or it can be 100 other zones, depending on how you want to, as a designer or a manager, tailor the water use across the site based on those different hydrozone factors. So if you've got large turf area that's all, I-40 rotors that have the same exposure, they're all the same slope, like in a park application, you may be able to water that entire park with just one sensor because it's really all one hydrozone. But then if you identify an area over in a corner that's got a little bit more shade exposure or a little bit lower in its grade, so water collects there, you may in the future identify that as its own hydrozone and put in an additional sensor that may monitor just that smaller area. So we try to make it as easy as possible to add sensors to a system based on identified need over time and experience with the control system.
Oh, fantastic. Got another interesting question on, just how proprietary is the whole system. I would assume it would work with any decoder, but just Tamara just asked, what all sort of other manufacturers' equipment would it work with?
Okay, that's an excellent question. With the sensors, they are part of our two-wire decoder system. So the sensor blade has a decoder that's installed or manufactured on the sensor blade itself. And with that two-wire technology, it's proprietary to baseline. So the baseline moisture sensor would not interface with another manufacturer's decoder system, just like their decoder or sensor technology would not work with ours. So it is proprietary, but we do have a device that you could reference on our website called an S100, which is a little add-on sensor unit that can be utilized with any manufacturer's control system that acts as a common interrupt.
Oh, cool.
But it's geared more towards smaller residential type applications than it is for managing a large park site or a larger campus application.
I gotcha. Okay, now this one, I think this will be a quick and easy one. But what about in situations where you have a very specific watering window, where you can only water certain times of the day or for a very small watering window? How easy is that to control?
Okay, so when we're dealing with water windows, there's two different questions there. One would be, when we are allowed to water, how do we water within a given water window? And then the other would be, if we're allowed to water on specific days, how do we handle that with the sensor? So when we're watering within a water window, on a lower strategy, the sensor will say, I need to water, and it will water for whatever time is programmed on those zones within that hydrozone that sensor is associated with. So you're able to have a very predictable water window because you have a specified amount of time that those zones will irrigate. When we're given the day of the week to water, the same would apply because we've got a known runtime for those zones. If we are operating on an upper threshold watering strategy where we're applying a variable amount of runtime to achieve a desired moisture content in that soil profile, then considerations would have to be taken into account with the programming as to how big that water window can be in order to get your watering done within them. And if it's not If your watering opportunity isn't open enough in order to fill to filled capacity, you may be able to manage to a level below filled capacity because your constraint is your water window as opposed to the amount of water that you have access to. So just thinking it through and understanding how the technology works and how to apply it, and working with a baseline professional in the programming and configuration of the controller can accommodate those.
Excellent. And then how about one last question? You showed some good pros and cons versus a weather station. But what about the cost difference between this and a site-specific weather station?
Well, weather stations come in all different shapes and sizes and price points. So there's highly instrumented weather stations available from different manufacturers that a municipality may invest in, that may be more accurate than a Brookstone type weather station that is at a homeowner's application. As it relates to baseline, we're using Weather Underground's network of weather stations to link to a controller and provide weather data to it. So there's no additional cost associated with the weather station to operate it with a baseline system. You just have to have the controller connected to the internet and able to connect to a weather station that's also on the internet. As it relates to soil moisture sensors, a sensor can be significantly cheaper than a highly instrumented, calibrated weather station and provide that real-time ET data that can be used to regulate those irrigation cycles.
Well, very cool. Well, like you said, you are certainly available for any further questions. If that spurred anyone to have any other questions, to shoot your way. Otherwise, thank you very, very much. This was really cool. Really learned a lot myself. I hope everyone else did. And wish everyone a good weekend.
Very good. Thank you for the opportunity, Jeremiah. We appreciate your partnership and our association.
You bet. Have a good one, man.
You bet. You too. Thank you. Bye.